Hello, my name is Gareth Rendle. I'm happy to present our work entitled On Virtual Pointing Arrays and Motion Artifacts, in which we investigate the perception and mitigation of motion artifacts that occur when using a pointing ray. Virtual pointing rays are a common interaction metaphor for selecting out-of-reach objects in virtual environments. The visualization of the ray projects away from the user to intersect with the seen objects, with the ray's direction typically controlled by the position of the user's hand. The direct mapping between the hand pose and the direction of the ray means that when the user moves the hand quickly, the ray can move quickly across the field of view. This fast motion can cause users to perceive several distinct copies of the ray, which you may even perceive in this video. These motion artifacts are known as multiple image artifacts. They occur when a strobing stimulus moves in relation to the eye, meaning that consecutive appearances of the stimulus on the retinal image are separated by a displacement that exceeds a fixed threshold. Instead of perceiving smooth motion, viewers perceive multiple copies of the stimulus. Pointing movements have been shown to start with a fast ballistic motion of the pointer towards the target. If the user's gaze is fixed on the target while this motion occurs, the ray stimulus is likely to move quickly across the retinal image and cause multiple image artifacts. In addition, the ray stimulus often has high spatial frequencies, which cause artifacts to be perceived at lower movement speeds. If the ray is brightly colored or contrasts with the background, then artifacts will be more noticeable due to the visual system's sensitivity to high luminance and high contrast stimuli. While there is a body of research on the perception of motion artifacts in general, the topic of motion artifacts in the context of virtual pointing rays has not been addressed. Accordingly, the first research question addressed in this work is: are motion artifacts perceived by users when selecting objects with a virtual pointing ray? If motion artifacts are perceived, we would like to find a way to mitigate them. A common approach to motion artifact reduction is the use of motion blur. Motion blur occurs when moving objects are captured by a camera because the camera's sensor integrates light contributions while the shutter is open, resulting in the object being smeared along its trajectory. In computer graphics, this must be explicitly simulated, since the scene is typically rendered according to the scene state at a single instance in time. Numerous methods for simulating motion blur have been proposed. The geometric substitution approach replaces a moving object with an extended geometric representation that captures its evolution over time, for example by rendering lines instead of moving points. Similar approaches can also approximate motion blur, for example by creating geometry that describes an object's motion silhouette, which can be rendered with an opacity gradient to simulate the smearing effect. Alternatively, motion blur can be applied in a screen space post-processing pass. So, given that we expect motion artifacts to occur when using a selection ray, and that motion blur is typically used to mitigate motion artifacts, our second research question is: can motion blur, applied to a pointing ray as shown here, improve visual quality during ray selection? Our motion blur implementation is a motion blur approximation similar to Jones and Keyes' motion silhouette approach. We adapt the method for pointing rays by creating a ray trail, taking the quads that represent the last n positions of the ray and joining their trailing edges, highlighted in blue. The trail is rendered as a triangle mesh, with the opacity varying smoothly along the trajectory of the ray. Additionally, the opacity of the ray is modulated according to its movement speed. When the ray is moved quickly, this simple motion blur effect reduces the luminance of the ray, removes high spatial frequencies, and reduces the between-frame spatial displacement of the ray stimulus, all of which are factors that affect the perception of motion artifacts. We designed a user study to test whether motion artifacts are perceived and how motion blur affects the visual quality during pointing. 15 people took part in the experiment. During each trial, they completed a simple selection task. 9 targets appeared in sequence, positioned on a circle. The participant had to select the visible target by intersecting it with the ray for 1 second. In our within-subject study design, participants completed a total of 32 trials, performing selection tasks with the motion blur effect on and off, different angles between targets, and with different HMD refresh rates. Additionally, halfway through the experiment, participants were given a primer on motion artifacts that informed them about multiple image artifacts and when they might appear. Half of the trials occurred before priming and half after. Throughout the experiment, we recorded the selection time and tracked the ray and gaze movement. After each trial, participants rated whether selecting objects with the ray felt smooth or shaky, that is, less stable. And after the primer on motion artifacts, they were also asked whether they noticed motion artifacts and whether they were distracted by them. So let's take a look at the results of our user study. Our first research question asks whether motion artifacts are perceived during the selection task. Here we see the distributions of responses rating whether participants noticed and were distracted by motion artifacts. We see a moderate perception of motion artifacts with a median response of 4, which was not affected by application of motion blur. Participants did not report feeling distracted by the artifacts, giving a median response of 2. As we expected a higher degree of perception of the motion artifacts, we took a deeper look into the ray and gaze movement data for an explanation. For meaningful analysis of the tracking data, we aggregated ray and gaze motion for every selection action performed by each participant. We calculated the rotation angle required to point to the active target and aligned selection actions using the time of the first saccade after the target appeared. This was averaged on a frame-wise basis across selection actions. Looking at the results for different participants, we can see quite a high degree of individual differences. Where some participants moved the ray soon after noticing the target, almost in tandem with the eye, others moved the ray later or slower. This affects the length of time that the ray is moving across the field of view, affecting the time interval when multiple image artifacts could occur. We can also plot the angular speed of the gaze, shown in blue, the ray, in orange, and the relative speed of the ray with respect to the gaze, in green. The horizontal dotted lines show the 30 degrees per second threshold at which previous work has shown that motion artifacts are perceived by 50% of participants. We can contrast participants 3 and 4 to see that relative ray speed also varies by participant, which is likely to affect the perception of motion artifacts. Since we observe fast relative motion of the ray with respect to the gaze in some cases, we conclude that the conditions for multiple image artifacts do occur during ray selection for some users. Individual differences in movement patterns could explain the moderate level of artifact detection on average. For some participants, the ray moves much faster with respect to the gaze. To test for connections between individual movement differences and artifact perception, we investigated the correlation between ray movement speed and artifact perception when the blur mode was disabled. The data hints at a positive correlation, especially if outliers are discarded. We plan future work with a larger sample size to shed more light on this correlation. We can now turn attention to the second research question, which asks whether motion blur can improve visual quality during ray selection. We have already seen that motion blur had no impact on the perception of motion artifacts, and we also found that there was no impact on selection time. However, we did find that participants rated ray selection as significantly smoother and less shaky when motion blur was present, meaning that overall, motion blur had a positive effect on how participants perceived selection. So, to sum up, we found that motion artifacts are perceived to a moderate degree by participants performing a selection task with a virtual pointing ray. During selection, some participants did move the ray quickly enough to cause artifacts, and we observed a trend suggesting that individual differences in gaze and ray movements are related to artifact perception. We found that applying a motion blur effect to the ray did not mitigate artifact perception, but did mean that ray selection was perceived to be smoother and less shaky. Our work therefore indicates that the use of a motion blur effect for virtual pointing rays has a positive effect on user experience. Our motion blur effect is available as open source for use by the community, with the link here and in the paper. Thank you very much for watching.